Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this 19th of October 2025, where we will be discussing Edmund Storms' latest paper, The Nature of Transmutation and its Relationship to Low Energy Fusion of Deuterium, in context with some other work. So, how is everyone this wonderful autumn evening here in Europe, and morning tomorrow in Australia, and in the middle of the day sometime over there in the good old US of A and Canada? How is everyone? And not to forget our South American friends as well. Hi Guyana Donkey, Ken Pratt, Omega, hi Overwhelmed Games, and we have Artifact in the house as well, Misunderstood, DIY Projects with Chauxis. We have Philip Power from New Zealand, excellent. And we have Joseph Collar also. Great to have you here, Misunderstood. Great to have you here. So, I quite like old people. I've said this before on a number of my streams. I have always really appreciated speaking to older people. And they give a perspective on life. They rationalize things in ways that young people are incapable of doing. They can look at things with the perspective of their years. They can also see sometimes, hopefully, if they've got a keen mind, where they might have got fixated on a particular idea and that might not be correct. And they can put at things in a more honest fashion. I guess what I'm saying is, as people approach their latter days, they become very, very honest. And that's different when your life depends on a particular story. Let's say your persona, what defines you, why you're employed, let's say, is dependent on a particular idea. And I just want to say a real thank you to those people out there that have supported the MFMP over the years, and also to myself personally through my blog, particularly in the last half decade near on remoteview.icu, because it is that support that has given me the independence to try and say what I think all of the time, rather than couch things because my very existence depends on it. So Guyana Donkey says, I'm with you, Bob. I used to work at a retirement house, and it was an amazing experience at 15-year-olds to get some, as a 15-year-old, to get some real perspective on life. Yeah, absolutely. I think, I worry that the youth and the young adults and even the middle-aged people of today are going to be moving into a scenario where they are less and less conferring with their elders, those within their family and outside their family, for advice and wisdom. And I think that will be a great shame for humanity, because it's not only the wisdom of hard facts, it's the wisdom of cultural aspects that are relevant, environmental knowledge that is relevant, food knowledge that is relevant just to your particular body. I think people, if I could give one piece of advice, and do it as you please in life, is to spend time with your elders whilst you can. Because they're not going to be there forever. And in light of that, there's one particular elder who essentially I'm pretty safe in saying is possibly the oldest member of the so-called cold fusion field that exists. Certainly in the West, I would argue. Perhaps there's some Japanese or otherwise Asian people out there that are older, but Dr. Edmund Storms is 94 and a half. In fact, next April, he's going to be 95 years old. And that is very good going even for a woman, but he's a man. And for a man that's worked with nuclear technology, one wonders quite how he's done it. And I think something that we can learn from is to have a rational mind. And I've appreciated in recent years, for instance, both the now late Mike McCubry, who knew Martin Fleischmann and was probably the most well-funded researcher in the field of cold fusion since its dawning, and one Dr. Edmund Storms, have in recent years given credit to the ideas of one Ken Shoulders. And that earned my respect. You know, some people do listen to people that have done things before and others don't. And I'm going to be approaching this particular paper by Edmund Storms here, The Nature of Transmutation and its Relationship to Low Energy Fusion of Deuterium, from the perspective of another great elderly researcher, one Dr. Takaaki Matsumoto, who also is sadly not with us now. I would have loved to be a fly on the wall in a robust conversation between Ken Shoulders, Dr. Takaaki Matsumoto, and Dr. Edmund Storms. I think that would have been a killer discussion. There isn't one of those people that didn't require of their intellect to make supposition and speculation, and then to go and look for the evidence, or to arrive at a particular hypothesis from the evidence that they had available to them. Now, Dr. Edmund Storms, he was 35 years at Los Alamos National Laboratory. He developed a fusion rocket propulsion system, was a key participant in that. That actually worked. It was developed, but it was never, as far as we are told, put into active service. That must be deeply frustrating for him, if that's the case. Of course, perhaps it wasn't the case. If you are to believe people like David Adair, he showed at the age of 17 a toroidal fusion-based propulsion system, and then was led to believe these systems already existed, at least in the universe. And of course, we know that that's Dr. Edmund Storms, received the documents from Chuck Bennett and Warren Cooley about the magnetohydrodynamic fusion ball lightning patent in 1995, before it was classified. So, you know, it's not out of the realm of one's imagination to think that they've had all these inputs, and in these latter years are trying to rationalize their experience of their life. Now, a number of years ago, there was another paper that came out in Nature, and this was by the $10 million funded Google team, and it produced this paper called Revisiting the Cold Case of Cold Fusion. Of course, it produced no significant positive results, and their aim was to embark on a multi-institution program to re-evaluate cold fusion to a high standard of scientific rigor. Okay, so they got everyone involved that had not been in the field before. They did not consult with the scientists that had worked on similar experiments, myself and Dr. Alexander Parkhomov and my good friend and colleague Alan Goldwater. When they did a study which used nickel powders with hydrogen, they used lithium aluminium hydride, and they produced this super fancy calorimeter here. Of course, we know that if you make everything the same temperature, good luck in finding any results. They did find that there was some interesting data when they changed the particle size over here, but because they had 3 above and 1 below, the average came out as a null result. And that is how averaging works. So that's a bit of a shame. Nickel surface treatment here, additional parameters. The problem we found, which we found actually long before this actual work started with that $10 million that was, in my view, completely wasted because they didn't attempt to learn from what was done, was in an experiment called BANG. And it was where we had lithium aluminium hydride and nickel in an alumina swage lock sealed vessel, and it blew up. And so you can actually go and look at the short version of that video on our YouTube channel called Bang. But what happened was Dr. Edmund Storms said he would be keen and willing to look at the core that we had extracted. And in those videos you can actually see it was recorded live, it was published live, you can actually see us extracting that core. And so yeah, we thought, excellent, we didn't have any access to SEMs or anything like that at that time. So we said, thank you, Dr. Edmund Storms, we will avail of your offer. And so we sent him the sample, and this is what he found. He found that the nickel, which was a carbonyl nickel, had basically sucked the lithium aluminium hydride, had decomposed and coated the material, the nickel powder. And I'm not entirely sure why my laptop is going very, very slow. Just bear with me. It's probably Adobe, because Adobe does that. So I will kill that file in Adobe. It's Acrobat. It just uses system resources. Okay, let me see what's going on here. Let me see what else I can dispose of it this time. Okay, why is that not opening? Okay, that seems to be better. So what this nickel was a type of carbonyl nickel. It was fibrous in nature, like this, and it had these kind of nanometric scale structures on here. So these spikes, and so you get energy concentration on the spikes and anharmonic oscillations, discrete breathers. Different names have been given to these things, where you get energy coming from different sides of the crystal structure, and they meet and create a kind of super wave as they get to the end. And this is what Georgy Messiatz indicated would cause an ecton to be released, which was his name for an exotic vacuum object, or an energy soliton structure coming off the end of these structures. Now, when it was looked at by Dr. Edmund Storms, this is what he found. And if you are to argue that you need to have hydrogen, and this is argued by several authors, to have hydrogen actually touching the nickel for it to actually work, how can you do that when you are covering it up with what essentially you'll see in a minute in Edmund Storms' analysis is metals? So the active structures that I just showed you, these spiky bits here, that are able to do energy concentration and pump that in and do explosive electron emission, that is prevented by these blobs. And actually this, along with Dr. Parkhomov's own experience, led him to completely remove lithium aluminium hydride from his powder mix and just go with treating the nickel and injecting hydrogen gas. I expect the author of this original concept to mix these two products, not that it wasn't original from the point of Pons and Fleischmann. Pons and Fleischmann used lithium aluminium deuteride actually in their experiments, but Rossi has this patent for a heater which used a combination of nickel and lithium aluminium hydride, and there was this assumption at the time that these were mixed together. What this particular experiment here indicated was that that was not the case, and that what you would have is the lithium aluminium hydride in a separate part of the reactor, and all that was a source of hydrogen that didn't involve you having to have a hydrogen bottle in there. And it was a bit like the 1930s, 20s or whatever it is, valve type devices where you would have a titanium hydride little pellet inside the valve, and then you would have a heater element in that, and that would heat up the titanium hydride and the hydrogen would be released, and of course when it cooled down the titanium would get that hydrogen out the atmosphere, and there was separate electrodes to allow for that. So essentially what he was doing was producing hydrogen in situ for the reaction to take place. Absolutely all of this was determined before Google spent $1 on their research with respectable universities, with respectable scientists. Had they asked us, they would have learnt from what was learned in the Bang experiment, and learned that mixing these two basically does not work. Okay? Now, you could argue that having the right structures here by choosing different types of nickel powder, yes, that would do something, but it wouldn't last for very long, and depending on how fast you melted your lithium and aluminium on there, then you would get it to shut down. Okay? So here are what we're seeing here. So you can see our nickel and our aluminium here, and he's using SEM with EDX, which doesn't see lithium. So if we're seeing aluminium everywhere, you can pretty much be sure that you are getting lithium there as well. There's just not enough electrons on lithium to be able to see in a scanning electron microscope with EDS. Okay. Okay. So what was shown? So I have Dr. Edmund Storms to thank for that. I wish Google had learnt from it. And as a result, Google wasted money. Okay, but I'm not sure that $10 million to get a negative piece of press in Nature about so-called cold fusion, whether that might have not been a good investment, I don't know. It'd be interesting to see what else they are investing in and make a judgment call on why. Okay. So yeah, so basically I have a lot of respect for the author of this paper, Edmund Storms, and as I said in my blog today, he was one of the first researchers that reached out to the Martin Fleischmann Memorial Project, and I have this very visceral memory sitting down with my laptop on the floor in Nicolas Chauvin's lab in EPFL in Switzerland, and with a tokamak nearby, with Mathieu Vallat there, and discussing our plans, having replicated Celani, Francesco Celani's work. It might have been actually in early 2013. No, I don't know. No, when was it? I think I basically came back from Rome, so it would have been December the 14th. Yeah, I think it was 2012. Anyway, you get like this as you get older. Yeah, so, and his presentation at ICCF 26 in Morioka essentially said that all LENR is enabled by electron clusters. And he had the grace to say, and the honesty to say, when I asked him, you said that this is the case, but of course electrons have the same charge, Pauli exclusion principle, how do you get these electrons to come together? And he mentioned the work of Ken Shoulders as one possible explanation. Okay. Of course, what you're going to see in this paper is a big discussion on transmutations and how they may, from his perspective, be possible. Last week, we were talking about a paper where there is no indications they have any intention of looking for signs of transmutation. And in fact, the Konrad Chersky reached out to me during the week to complain about the fact that I had talked about that paper in the way that I did, with no mention that he would be willing to accept my offer to look at the samples, the targets for transmutation, or that they would do that themselves. As I predicted, I don't think they would have any intention of finding out that their theory could not explain the observables. So the best way to make sure that your theory is not challenged by your actual experiments is to not look at all the data. I still appeal to them to not fall into the bucket of fooling people and possibly even themselves by not looking at all the data. Now, even this work by Dr. Edmund Storms is looking at, from his perspective, in the way that he looks at the data. Anyway, without further ado, we'll start looking at it. So, the nature of transmutation and its relationship to lone diffusion of deuterium, Edmund Storms, Santa Fe, New Mexico. Okay. Topics: transmutation. There you go. There is the first word in this paper. It is transmutation. Here we go. And so he's not holding back. It's definitely transmutation. The second word, not the first word, the second words are cold fusion. Of course, we call that coherent energy transformations now. A new nuclear mass of, well, this doesn't actually have a name. This thing does not have a name. Now, the normal hydrogen is called protium. Add an extra neutron and you get deuterium. Add an extra neutron and you get tritium. And add an extra neutron and what would you get? Well, you'd probably get quadrium or something like that, if you're following the sort of kind of logic. But it doesn't have a actual name, but it is known to be able to be produced in particle experiments. This isn't what this is, according to one Edmund Storms. And also, it is the basis for Brillouin energy technology. They are arguing that in their hot tubes, and this is one that's funded by Carl Page, who is actually of Google fame. His brother is Larry Page. Partly funded. They believe that the protons in the system are, through shock and I would argue electrostriction, being compressed to form deuterium, then tritium, and then, as we're going to call it now, let's say quadrium, and that then the quadrium decays and you get the products from that. If that is the case, that is doing something like electron capture. And that is also what is suggested by Dr. Edmund Storms, as you will see, as the key reaction going on in here. Now, what is electron capture? Well, it is a weak interaction mediated nuclear process, which means it falls into the purview of the concepts of the reactions proposed by Dr. Alexander Parkhomov. And we have a reaction calculator for that. And that reaction calculator is at LENR. No, it's not. I'll get there in a minute. It is at, let me find it here. Okay. Get it up here. The one you know and love and Philip Power is on the stream tonight, so he has brilliantly programmed this. nanosoft.co.nz. Now, in this reaction calculator, you see me use scores of times. We can go to fusion reactions here, and we can go protium. Okay, you can go protium, and we'll do protium and deuterium here, and you'll see the spread of isotope that come out. Okay, so protium and deuterium. I'll go in even bigger, so that's what I've got there for those that can, hopefully you can see that. And we go execute query. We'll remove the limit there. And we've got neutrinos left and right here. That'll allow for some weak interaction here. Okay, so 2 deuterons fusing together, we get 4 helium. Okay, now last week we were discussing, both from Matsumoto's perspective and from the team at Triton under the European funded project, that this is energized and excited to 23.8472 mega electron volts, and that under the theory of Matsumoto, this excitation energy will have to be released, and that's at least by the production of a positron and an electron. He also argues that a neutrino comes out of that, producing a thing called an iton, and the Stichin paper argues that that doesn't exist. Although they don't even address it. If you've got proton here and deuterium, again with no neutrino involved, you get helium-3. Again, this you would expect this also to be highly excited. But this is the reaction that you're talking about down here, is hydrogen plus hydrogen, or protium plus protium specifically, atomic protium and protium, goes to a deuteron with this energy, which is not massively large relative to this massive amount of energy. And then we've produced a deuteron, and we can then fuse a protium with a deuteron or deuterium atomic to a tritium, a triton. Okay? And of course, you know, if we put in a triton in there here, now the Parkhomov reaction tables do not actually do, actually that needs to go in the other. You need to put the heavier elements over here. Okay, heavier element isotopes. It's lighter on this side, heavier here. Okay. If we have a triton in there, we can take a protium and a triton, and we end up with helium-4 here. There is the intermediate production of, following the logic here, that we get hydrogen go to deuterium, deuterium go to triton. If we have a hydrogen and a triton, protium and a triton fusing together, you will, by the same logic as these two, you will actually get quadrium 4H produced, and this will then decay to 4 helium. Okay, it does that by beta decay. You need to have one of those neutrons decay. Okay, am I right in saying that? Yeah. Okay, so that would be the overall process, but we can't see quadrium here because these reaction tables do not like to produce any. We've got a few things that LENR can produce, and we know that LENR produces tritons, so we have that in the reaction tables. Now, I have a new table system that was built off our work. That is myself, Dr. Alexander Parkhomov, and Philip Power, who is here. And I can announce this today. And it is being built, and it's currently being built, and we would like you to go and have a look at it, but it's being built by one Brian White. Thank you for your volunteer time here to do this. And it is at LENR Academy here. It's at LENR Academy. So you just type that in. This is what we end up with. And this is the Nanosoft package And this is updated so that it's responsive. So if we scale our thing here, it will work on your phone, it will work on your mobile devices, your tablets, as well as your laptops. And so it's responsive, that you can drop things out. It's a really nice little interface, and he's starting to add in new touches and approaches to working with the data that was produced by Dr. Alexander Parkhomov and Philip Power. So if we go to our fusion reactions here, it's actually more intuitive. You can use this like with a touch screen. It's quite nice. We can go protium, deuterium and tritium. We can add those in as products, as input product reaction elements. And we can go over here, we'll go protium, deuterium, tritium. We can get rid of these. And actually it downloads the database and it instantaneously gives you the answers down here. Yeah, it's got different modes. You can go into light mode here and dark mode, yeah? Okay. You know, it's funny because when I built the MFMP's website in 2012 in 4 nights, 3 days and 4 nights, everyone mocked me for making it in dark mode, and that's because I was using professional animation software, and if you're staring at the screen for a whole long time, you want dark mode. And everyone said, why didn't you make it white? And I said, well, it burns my eyes every time I look at it, so I'm going to make it dark, and I'm sticking to it because I use professional software and I have to look at the screen all day. And then the world went and looked at dark. So the great thing is he's built this heat map here. And also down the bottom you can see isotopes. So if you just want to find things that are seeing helium-4, you can click on that and it shows you the reactions that are seeing helium-4. If you would click on helium-3, it'll give you the reactions that are producing helium-3. You can turn off the boson fermion type, so you just see the key aspects here, the inputs and the outputs, and also the energy and whether it's a neutrino involved. So we take that out, put that in. So there we go. And so it's really rather nice. There we go. So if I add in tritium here, we might get some helium coming in, although I don't know. Let's see. Not helium, lithium. There you go. So lithium's being made by 2 tritons coming in here. Now, I think there's a little bug down here. The now appearing doesn't work there. So, like I say, it's in development. But if there's things you want to investigate, I'm gonna switch out of that, and maybe it's got some caching issue. We'll put that in. It might just be because I've clicked on things. Yeah, it remembers things in the heat map. That's the problem. Okay, so I'm going to go here, protium, deuterium, tritium, and then I'm going to go here, protium, deuterium, and tritium. Turn off these 2. Okay, and hopefully we're going to get there. So we've got lithium there. These are the isotopes that are in the reaction table. Yeah, it's still emptying. Yeah, no, it's not showing the results there. So Brian, you've got a bug there. Anyway, I'm good at finding bugs. And so I want you to try and engage with Brian on this because I think this is very powerful and easy to understand. Okay, and you've also got like your element data in here, which you can pick up. So we can actually look at hydrogen here, and or let's go to tritium. Let's go to tritium and turn that off. See, it remembers these things from other windows, so you just have to be careful about that. Okay, yeah, okay. So anyway, I'm still learning it because he's adding features daily. Yeah, brilliant work, Brian. Really brilliant. Okay, so at the moment, definite results here in one table. And typically I would grab these and put them into my blogs, as I've done over many moons from here. But when you are doing reactions in here, if I go back to fusion reactions here, let's try that again. I'll turn those off, clear all, and we will go these 3, and we will go over here, and we go these 3, okay, and yeah, okay, so it's now cleared it. So we've got lithium 6 over here. So I click on that, it'll show you that the lithium-6 is being born from 2 tritons coming together. He's got these nice radioactive symbols here to show that it's a radioactive isotope here. And there you get plenty of energy out of that. Yeah, it's not forgetting that when I click off it. So there's just a little bit of a bug there. Has it come back? No, it's still there. Oh no, I must click up here. Okay, so those. Oh right. Okay, so if I click down here on this lithium, then it appears up here, and if I unclick it, it doesn't disappear from there. You need to unclick it up there. Okay, so we've got all of our reactions. So that's what the bug is there. It needs to. If I click this again, it needs to deselect. So Brian, that's a bug for you. That's a live bug fix there. We need. Okay. Yeah, you need to untoggle. I understand, but if we come down here, Brian, and I click on lithium-6, I want to untoggle that, but it doesn't untoggle it. I have to go up here. Okay. So anyway, I'm pretty sure that's going to be an easy fix for you. Anyway, you can see, so let's say we want to find those reactions that produce helium-4. Here we go. We've got a protium plus a triton, gives us helium-4, and I'm arguing that this reaction will actually initially produce, by the same logic that the other ones work, that is to say, the other ones work by, so for instance, deuterium, it's fusing these together, okay, and these coming together to make tritium, okay. This here, hydrogen, deuterium, sorry, deuterium and deuterium should make, well, actually, if it's a tritium, oh god, now it's not showing me that. See the tritiums. The hydrogen and tritium should make quadrium. Yeah, okay. I think you get the idea. Anyway, go and have a look at this. See if you can do some bug testing. Please reach out to the author, Brian, and ask him if there's any little features you want added in there. That would be fantastic. This is why you do things openly and you share things so that things can move forward. If you're not moving forward, you're moving backwards. Okay, we might look at this again. We may not need to. Let's go back to the paper of the day, which is this by Dr. Edmund Storms. So, abstract. Elements that are absent in a material have been found to form during low energy fusion of deuterium. So, this is exactly the fusion or in a metal that was being talked about in the paper last week, where there is no evidence. They're not even looking for evidence, and it would appear they have no intention of looking for evidence of transmutation, which is the first word here, and it's the subject of the very first sentence. So the first word in the topic, it's the nature of transmutation, and the first sentence. I think this is very good of Dr. Edmund Storms. He is saying, yes, transmutation occurs. Now, he's saying the transmutation process can be explained by assuming the fusion reaction involving deuterium emits a 4H, we call this quadrium particle, with enough kinetic energy to produce the reactions. So if you take your Z number of your element and your A number, it's taking quadrium in, it's throwing out 2 neutrons, and you are getting a proton, which is coming from the proton in the quadrium, and another neutron adding 2 to the A number. Okay, so effectively it's adding a deuteron out of the quadrium and expelling the 2 neutrons. When it encounters a nucleus in the surrounding chemical environment, this proposed mechanism is examined in light of several published studies. Okay, my question is he's saying 4H here. How the hell does that form? How the hell does that form? I don't get how that forms. And then up here he says 4H plus. Now I can kind of see how 4H plus would form. What am I talking about? When you get 2 deuterons coming together, you know, it's got to have electron capture. You're effectively saying that one of the protons is capturing an electron and forming a neutron. So effectively you've got a 2 neutrons fusing with a deuteron to produce 4 hydrogen, and of course you lost an electron, so you end up with a positive thing here. I guess that's what's going on, right? The fusion of hydrogen isotopes is found to occur spontaneously within specific sites in certain material. Here we go. Spontaneously within specific sites in certain material. Now, Dr. Edmund Storms say it's in what he calls the nuclear active environment. What is that? They are basically all of the areas identified by Georgy Messiats in his 1996 paper, but learnt many years before, I think in the 1970s, in his exploration of what he called ectons, which are exotic vacuum objects. So if you go and look at his presentation in 1996, this is Georgy Messiats into ectons. He talks about cracks, he talks about spikes, he talks about inclusions, he talks about grain boundaries, he talks about all these kind of things going on. All of the main ways that people have tried to enhance the process of what we're calling coherent energy transformations was in that paper in 1996 with regard to ectons. Most specifically in the work of Dr. Edmund Storms, he's talking about this nuclear active environment, which are these cracks and maybe grain boundaries and things like that. That is very similar to the work of Dr. Takaaki Matsumoto, who specifically said it's either on the surface in small cracks or holes inside the metal lattice or between crystal grain boundaries. Why would it be there? Well, on those areas you get an abundance of electrons in a metal. A metal is kind of like a solid plasma, and you get this sea of electrons, conduction electrons all over the surface. And you can imagine that you've got two surfaces in a crystal grain boundary, so you've got a larger chance of having more electrons in there. And the idea is that if you're electrostatically driving hydrogen isotopes into a metal such as palladium, which is the element which was Thomas Graham FRS established in 1876 or something, that it stores the most hydrogen. There was no understanding of deuterium or tritium back then, and that hasn't changed. It's like a 1-for-1 ratio it can store up to. That's like in those crystal grain boundaries, you can imagine that some of the hydrogen's isotopes, they will diffuse into those crystal grain boundaries, and you might get an aggregation of those alongside all of these electrons. So there are similarities with what Dr. Edmund Storms is suggesting and Dr. Takaaki Matsumoto is suggesting in their respective theories. Okay, so go back to this. This reaction produces measured energy and observed nuclear products consisting of helium and tritium. Professors Fleischmann and Pons, University of Utah, first described the events in 1989 to occur in palladium deuteride when electrolysis was used. Since then, this nuclear reaction has been replicated many times using other treatments, with the production of other elements not initially present in the material. So here we are, we're in the introduction, we're not even past paragraph 1, and again, he's talking about transmutation. He's talking about transmutation. Why is it so hard for others to want to discuss transmutation? Well, it's probably because their theory doesn't allow for it. This additional nuclear process is called transmutation. There we go. All right, it's just reinforcing that in case you didn't get it, which is proposed to result from the energetic fusion product causing a nuclear reaction when it encounters nearby nuclei such as palladium nucleus in the surrounding palladium deuteride crystal structure. This paper explores the relationship between these two types of nuclear reaction through the involvement of quadrium, an unstable isotope of hydrogen containing 3 extra neutrons. But first, some background information is required. Helium-4, that's 4 helium gas, is an observed nuclear product resulting from the fusion reaction when deuterium is used, with the mass change resulting in a calculated energy release of 23.84 MeV. We talked about this last week. How does that get out if we're producing directly to helium-4? If that's actually occurring, how do we get this energy out? The measured values for helium energy ratio are compared in figure 1. And so here we go. This is what you should get. This should be the DD fusion energy up here at 23.84. But unfortunately, McCubry measured the energy down here at around about 20 MeV, which is something that we were discussing that had been established by, or referred to by Dr. Takaaki Matsumoto last week. Histogram of measured energy, and this is the value by Makubri. So remember I mentioned him earlier. Mike Makubri sadly departed very recently, I'm afraid. So the displacement, the average measurement from the calculated value obtained from the mass change is proposed to result from some helium being trapped in the palladium deuteride structure and a smaller amount lost during the transmutation reactions. Okay, so they're saying that transmutation and some energy is being lost in these particles, and it's because of trapping, because helium shouldn't come out. It shouldn't come out, and this is very, very important. How is the helium that's supposedly being produced in the lattice, how is it getting out of the reaction site? And in fact, Matsumoto goes into some detail to say, look, some people failed in doing their palladium deuterium cold fusion experiments, because if you load into palladium and then you let it degas, it doesn't go into it, but you get this thing called hydrogen embrittlement. The gas sort of comes out, or it goes into the crystal grain boundaries, and it literally smashes the metal up. And if you're relying on very small gaps or cracks in order to produce the reaction environment, and those gaps are widened or cracked apart, then it won't work. So you could find that, I haven't got a lot of budget, I'm going to start with my palladium electrode, I'm going to load it, nothing happened, I'm going to walk away from the lab, go home, have a weekend, come back, I'm going to load it again. Oh, it doesn't work, Oh, my experiment never worked. Well, it didn't work potentially because on the first loading, you didn't get the loading ratio right, and then it cracked up the electrode, and it would never work after that. It would never work after that. And do you know how you learn that? By deeply studying the electrodes. You have to deeply study the electrodes. If you do not look at the working material between experiments, you're not going to know what's happened to it and if it's the same. Okay? And Matsumoto caught on to that. Nevertheless, the good agreement between the measured values and the value based on the mass change indicate that helium is the major fusion product. Okay, so they're assuming that helium is the major fusion product. How the resulting energy is dissipated is the next problem requiring a solution. So because another emission is required to conserve momentum. Yeah, this is the point. You can't have the momentum conserved with just one thing. Something else has to come out. And in the work we were discussing last week, they were arguing it was a positron-electron pair that was produced by internal pair production. Internal pair creation, and Matsumoto argued that it was basically that and or something that included neutrino. Okay, this problem is explored greater detail by Storms in this paper, in another paper. When kinetic energy of the emitted fusion product is measured, an unusual feature is observed. Two independent studies describe the emission of ions having a series of energies, with each having a consistent value from one to the next in a series. These two studies are compared in figure 2. Okay, I won't go into the detail here, but Storms and Scanlan demonstrated that the emissions are an isotope of hydrogen, not helium. They demonstrated that. Storms suggested that the observed helium could be explained if these emissions are actually quadrium plus, with the observed 4 helium gas being formed by beta decay after most of the hydrogen isotope had diffused out of the material in which the fusion reaction had occurred. The idea is explored below. Okay, so basically he's saying this is produced in the material, and it's a known fact that in hydrogen-absorbing materials, the hydrogen isotopes can move around. There's just one itty-bitty problem with that when it comes to quadrium. Tritium has a half-life which is in the over 10 years, or around about 10 years, okay? Deuterium basically stable, well, it is stable. Protium stable. But quadrium, it's not so stable. It's not so stable at all. Anyway, we'll come on to that. So showing the kinetic energy of the claimed 4 quadrium emissions resulting from the fusion of deuterium. Right, so there's various kinetic energies he's observing here. I need to study the chart before I understand it fully. Anyway, the claim for the emission of quadrium has created many objections because this isotope is thought to be very unstable. Here's the point. Decomposing by the emission of a neutron to form tritium in 10 to the minus 22 seconds. 10 to the minus 22 seconds. That is a very, 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 very short amount of time. I'm not sure that that is long enough for that hydrogen isotope to whittle its way and through stochastic interactions and whatever, being the biggest of the hydrogen isotopes in there, out through a crack and come out and live long enough to be converting to the helium. Okay, this behavior is observed when the tritium in palladium, tritiated palladium is bombarded by energetic neutrons. This right here is a standard beamline experiment, the kind of thing that we were talking about last week. Yeah, where they were firing deuterons into zirconium deuteride. Okay, this is in Triton's tritiated palladium, and it's being bombarded by a deuteron stream. The resulting generation of energetic particles is claimed to be caused by the brief formation of unstable quadrium nucleus, instead of by the fragmentation of D or T. Okay, I see where it's going. In contrast, if 4H quadrium were to form with less applied energy, that is not in a beamline situation, this reference, Gurov, speculate that metastable states may exist. This is a speculation right here. We have speculation going on here, right? So from this point on, we are talking about speculation in its nuclear structure with the ability to support unexpected behavior. A variety of observed behaviors described below invite further conclusions about the nature of quadrium. For example, the quadrium plus emitted by the fusion of D has enough kinetic energy to cause nuclear interaction when it encounters a nearby nucleus. Right, so they're saying this isn't a standard beamline experiment. This isn't bashing particles together. This is happening within the nuclear active environment, in the material. It's producing something that isn't unstable to the tune of 10 to the minus 22 seconds for its decay. This is something that is actually more stable. It's metastable, but it has got energy and it is shooting out. And when they're referring to this 4 plus H, okay, so it has, by the fusion of D, it can go and form transmutation. Consequently, such a secondary nuclear process can reveal important information about the nature of fusion reaction. So actually, his theory is now relying on secondary nuclear process. Okay? Typical spectrum produced when cold fusion occurred during gas discharge, D2 plus H2 gas. Okay. Justification for quadrium involvement. The proposed role of quadrium is supported by 4 observed behaviours, with each being logically consistent with each other. Although these patterns of behaviour are not proof, they suggest that quadrium plus is the initial emission resulting from the low energy fusion of 2 deuterons in a material. This process would predict the emission of very energetic electrons. Would predict the emission of very energetic electrons as 4 helium forms. Okay? Whoa. Whoa, whoa, whoa. Steady. Hold on a minute. Now, what I haven't been telling you is what I thought when I read the title of this. What was the title? Sorry, not the title. The subtext on the topics. Here. When I was reading this, I read this. And then I read this, 4H. And why that interested me was this was basically all over Takaaki Matsumoto's theory. Of course, he wasn't afraid of transmutation. Right from the outset, very early on, he was observing large-scale transmutation in the systems he was investigating. So let's go and take a look at some of the things that he was saying. Now, we have the old 1-for-1 book, but we also have the updated book, and we're going to look at a couple of updated images taken from his original materials that we've now scanned in a better way, and you will see very clearly that he's seen things that no one else has seen that informed his understanding. Okay, so let me just pull this up. And where we got to I'm just gonna run through a few pages here, and you'll see where I'm coming from. Okay, so Nattoh model. What have we got here? So he's looking at the standard reactions here, but the reaction that seems to be produced most of the ultimate products are for helium. But he's arguing that this is a hydrogen catalyzed fusion. Okay. A hydrogen isotope catalyzed fusion. We're going to show where I think, hopefully, after what I've given in this particular segment, you will have a better understanding of where mentally he was coming from in his hypothesis. And it's not too far removed away from what Dr. Edmund Storms is saying, except in Dr. Edmund Storms' case, he's thinking about a linear oscillation between in a crack or in a crystal grain boundary, and what Matsumoto is thinking about is a more of a volumetric structure. And he steps into this from the most basic case where you need the deuterium gas effectively and another deuteron there, or monatomic element in there. So he's then trying to explain the observables, and you can see various reactions there. And then as his work progresses, he then does this. So if this is the first one we think we're going to get, what happens in ordinary water? Well, he says you should get 2 helium produced here. Well, what is that? That is literally electron capture going on. This is electron capture here. So both Edmund Storms and Takaaki Matsumoto are suggesting there must be a weak process going on. This is textbook Alexander Parkhomov. The predominant process is hydrogen catalyzed fusion reaction given by reaction 2 here in normal hydrogen. Okay, and then he goes, the 2 helium decays to a deuteron and a positron. Oh, here we go. We've got positrons here. Of course, we're starting off with light water here. The high energy particles such as positrons, deuterons, and protons are emitted. So we have protons here, and we have positrons here, and deuterons here are emitted. These particles make surrounding atoms in the sample excited or ionized, which results in X-rays being radiated. Okay, so we've got some X-rays. Moreover, the positrons annihilate with electrons to emit gamma rays of this. Oh, that's interesting. Where have we seen that before? Anyway, we'll go on. Okay, blah, 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 blah. So we actually saw this paper last week. For heavy water, on the other hand, it's predicted that a new particle ion would be emitted in the reaction in the 20 MeV range. Okay, so the 20 MeV range is this observation by McCubrey. Okay, so here we look at this paper. Now, these papers were out of the order that Matsumoto wanted to release them. It was how they were selected by fusion technology. So it was a bit of a challenge for him. When the Nattoh is formed, we get this. Electrons connecting hydrogens are also pressed extremely close to the hydrogen nuclei. In the hydrogen nucleus, the depolarization takes place by inverse beta decay. This is a weak interaction. Okay, proton becomes a neutron, a positron, and a neutrino, and then you get these positron and electron when the neutrino forming an iton and EV. Okay, right. So why is this relevant? Why am I going on about all this? Because of this. Now we can see the emission of itons during the hydrogen catalyzed fusion reaction. The fusion products must be modified by the Nattoh model. When a single iton is emitted, one of the two fused hydrogen nuclei is fermented. So what do we get? If we have a deuteron plus an electron plus a deuteron, we get quadrium plus an iton plus a deuteron nuclei. And then this is what we see in the work of Edmund Storms. This is literally it. The quadrium then decays to helium plus an electron and an antineutrino. This is weak decay. This is a beta decay. This is the beta particle. This is the antineutrino from the decay of the neutron to a proton, producing helium from quadrium. Okay. So right there you have quadrium talked about, and here in this case he can say there's another mode by which it can produce not only quadrium in the location of its formation, but it can also produce a quad neutron, plus your iton plus a deuterium nuclei. Now, what's happening here is the energy of production here of this quad neutron is going to eject this iton and this deuteron. Well, that deuteron, what can that do? That deuteron comes out at high energy, and that can impact nuclei in the surrounding area and produce all of the deuterium-based transmutations that is being claimed by the work of Dr. Edmund Storms here. Do you understand what I'm saying here? Is that Matsumoto is saying you have to have at least 3 in the environment for this process to occur. And the actual process is catalyzed. And I'm going to walk you through kind of how that would happen. Okay. Now, this is true of any system that could compress these working materials into a small space. If you could squeeze stuff into a very small box, not electrostatically, but let's say, I don't know, into a phase singularity of a fractal toroidal structure, then that would do the same thing. You would have to have at least a deuterium and a deuteron in there, squeezed into that little small box. And of course, we know that both Ken Shoulders and Dr. Takaki Matsumoto eventually came to what ball lightning is, and we know from the patent that was shared with Dr. Edmund Storms that the magnetohydrodynamic system was doing its fusion that was driving the process and also enabling it to self-contain the fusion energy was happening in the phase singularity, as I have demonstrated over many times. So what I'm trying to say is we're looking at early 1990 and 1991 work of Matsumoto right now. And right back then, he was talking about the production of quadrium. This is literally 1990, 1989, 1990. Here we are, 2000, 2010, 2020, 2025, right? 35 years later, and in the most recent paper of the most senior researcher in the field, he's saying it's quadrium that's involved. But he has a different view of how the quadrium is produced. He's saying that deuterons are the things that are doing the transmutation, and right here we have deuterons being spat out at high energy from something that is neutral. And the great thing about neutral is if it doesn't decay, and we do know that normal neutrons have a long enough half-life to be able to exit a reaction before they decay into a proton and a free neutron, that is, into a proton and an electron and an antineutrino, then you could imagine if something similar is going on here, or if it was encapsulated in an otherwise neutral structure, it could come out of the material and do what he actually observed on emulsions, what we have observed going on in other systems as well. And so the neutron could come out, but the initial reaction energy that produces this, the quadrium or the quad neutron, emits a very high energy deuteron, and the deuteron would then go and do all the reactions we're going to see in the work of Edmund Storms. Here, the neutron nuclei can be considered to decay as follows. A quad neutron decays to quadrium plus a positron, plus an electron and an antineutrino, okay? So this is the first decay. And then this decays again to 4 helium, and we get another electron out and another antineutrino. So there we go. If we have a 2 neutron, it decays as thus. Now, Why is this relevant? Well, we're going to see ultimately. If you get full-on gravity decay, this is beautiful. You get matter converted into neutrinos and antineutrinos, whether it's from heavy or light hydrogen. This is complete matter collapse. Okay? Complete matter collapse. So before we get on to the next one, are we going to talk about this? Yeah, so he's talking about the energy and oh yeah, I have to show you this because this is the basis. This is the paper that we were talking about last week, but this is the key diagram here. Okay? And he's talking about semi-classical explanation of deuteron compression. Now, why is this relevant? It's relevant because of a particular thing, which is a real thing. It's not a made-up thing. It's a real thing. And you may not have heard of it before, but you're going to hear of it right now. Well, in a few seconds anyway, at least. if I can find my particular page here, which I had it on. Give me a second. Okay, what did I do with that? Okay, I might have put it in there. Give me a second. Can I remember? No. No, it's not there. Bear with me just a second. I'm trying to find something. Go and have a play with LENR Academy, the nuclear reaction calculator. I'll be with you shortly if I can find what I'm looking for. Where have I put that now? That's what I have when you have about 1 billion tabs. Okay, here we go. Here we go. Right, okay. Hopefully that wasn't too long for people. What happened there? It's back in here. So we need to go here. There we go, this one here. What are we looking at? When I am showing you this here, over on the right here, this little structure here, I am thinking of something that is a real thing. And it is called the H3 plus ion, or the trihydrogen cation. And what do we know about the trihydrogen cation is? It's the protonated molecular hydrogen. It's a cation, positive ion, with a formula of H3 plus. H3 plus. Okay? Consisting of 3 hydrogen nuclei, protons, sharing 2 electrons. The trihydrogen cation is one of the most abundant ions in the universe. One of the most abundant ions in the universe. It is stable in the interstellar medium due to low temperature and low density of interstellar space. The role of H3 plus plays in the gas phase chemistry of the interstellar medium is unparalleled by any other polyatomic ion. Okay? And it forms an equilateral triangle. It forms an equilateral triangle. There's a para and ortho version. So you've got hydrogen A, B, and C. You can start to see where he's getting the idea for his proposal for how this actually works. You can see it? Can you see it now? Can you see it now? Can you see it? A, B, C. We got A, B, C, A, B, C, A, B, C. Okay? One of the most abundant ions in the universe. This is not a fly-by-night assumption. Okay? Now, where are we? The trihydrogen cation is the simplest triatomic molecule because its 2 electrons are the only valence electrons in the system. It is also the simplest example of a 3-center 2-electron bond system. It was discovered by J.J. Thomson in 1911. Blah, blah, blah. there are all kinds of isotopologues. Okay. There's our diagram again. You've got your 0.90 angstroms here. Formations, and then there's all kinds of chemical reactions that occur, and so on. So this is our trihydrogen cation here, and it is basically a equilateral triangle. And if I go back here, you can see, where is it? Here. These are energy diagrams here. Maybe I'm going to get it here or not. Is it going to give it to me here? There we go. Da, 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 da. I got a, is it going to, oh, there we go. Beautiful, eh? And it's a flat plane thing where if you look at it on the side, it looks like 3 hydrogens in a row, but it's not. It's in a equilateral triangle. Okay. Do 2 fuse to carbon? Well, I think 3 might do. But, you know, with a lot of electron collapse, yeah. And this is the point, is that Matsumoto initially was thinking 2 bits coming together. Then he realized what to explain the actual physical data we're seeing. He was saying that, well, then vast numbers must come together. He talks about, you know, the case for 2, 3, 4, 5, 6, whatever. You can see that in his papers, but then it becomes a statistical nightmare to think about it all. But he does say later in his work that he recognizes that something is formed in which vast numbers of nuclei are simultaneously collapsed. Okay, but the logic starts with a minimum of 3. The logic starts with a minimum of 3. Okay, and so what is that logic? Well, I kind of skipped over it last week, but we'll look at it now in a little bit more detail. It's this. Let us consider a situation in which a molecule of the A and B deuterons exists in a highly pressurized space, a hole, such as the grain boundary of a polycrystalline metal. Now, the third deuteron, C, is assumed to enter into the space. As a result, the pressure increases to a value that is higher than critical. So you've got this little itty bitty bitty crack, there's just a deuteron in there, deuterium sitting in that crack already. And now what's happening is there's another atomic hydrogen coming in, or atomic deuteron, and it's coming in, and it's managed to get into that space, and the crystal lattice is squeezing it, the electrostatic pressure is squeezing it, and you've got all these electrons around the outside, the sea of electrons on the metal, on the actual crystal grain boundary, all around this thing, okay? And then he goes on. Now, as the third deuteron, C, is assumed to enter the space, as a result, the pressure increases to a value that is higher than critical. The electron combining the A and B deuterons is pressed by the invasion of the C deuteron. So A and B, the electrons that are combining these, are compressed because this comes in. It has to, okay? So that then the effective mass of the electron increases. So because these are compressed and pushed together, the mass goes up. That's how this works. Shortening the distance between A and B, so that A and B come closer together. Unlike the muon catalyzed fusion reaction, a symmetry exists in the hydrogen catalyzed reaction. The distance between A and C deuterons, here and here, is shortened as the B deuteron approaches A. So as B comes to A, this has to shorten. Okay? This also shortens the distance between C and B deuterons. So C and B come together. Okay? You get the idea? Therefore, the deuterons are compressed to an extremely small cluster by the compression effect of the deuterons themselves. We call this, and scramming is the wrong term here. He later uses, I think it's a mistranslation, and we've updated it for the new book. We call it a bunching effect because he refers to a paper that he proposed to the Atomic Nuclear Energy Authority, that international, where they use the proton beam and electron beam, and they use the proton beam to produce proton bunching and the electron to produce electron bunching. So it's bunching. So they're compressing together, okay, to produce these structures. It says the second stage is the deuterons gather so closely that the iton can connect them. The distance between the deuterons is expected to be extremely short. The limit for the distance between the deuterons is 3,672 times that of the intramolecular distance, or 0.7 of 2 times 10 to the minus 12. In this situation, the electrons move with the same velocity as the deuterons. If the range of the new nuclear force is assumed to correspond to this value, the rest mass of the iton is found to be 26 mass of electron. But he says that to actually start the process, you only need to exceed 2 times the mass of an electron. Okay? The rest mass of the iton is considered to be this. And that, when you have greater than the 2 times the mass of electron, this allows for the distance between the deuterons to drop to the distance of the strong nuclear force. The nuclear force here. Okay? And therefore you will get fusion to occur. All right, so that is a rough kind of overview, and it is based on simple understanding of a real thing in nature, which is one of the most abundant ions in the entire universe, and that is the trihydrogen cation. The trihydrogen cation, okay? Now, if you go back to Matsumoto's work, he goes on, as I showed you earlier, you can have... well, it depends how many deuteriums are coming into the same place, okay? So if you've got this and that, and then it shows the energy of the things that come out. Anyway, I don't think we need to go on right now. Okay, so this is what I'm saying about looking at the electrode and seeing some damage to occur to it. He actually did this, and we're going to pause on the next one. Okay, yeah, this is absolutely critical, but we'll move forward with the paper by Edmund Storms here. Okay. Justification. Although these patterns of behavior are not proof, they suggest quadrium plus is the initial emission resulting from low energy fusion of 2 deuterons in a material. This process would predict the emission of very energetic electrons as 4 helium forms. An emission that might have been detected by HOMLID. So again, this is a speculation. He's trying to say that the things that HOMLID are seeing are coming from the energetic 4 helium. In the model of Matsumoto, there is another loss process before you get to the formation of quadrium, because you have the process actually produces, let me go back up, up here. Firstly, we get this deuteron here, deuterium nucleus that can come out and do nuclear reactions, and this iton, and they can carry some of the reaction energy away from the formation of the for the quadrium. And then when the quadrium decays, you get the electron, and this is the high energy electron that is being talked about here, okay, by Dr. Edmund Storms. However, the observed electron emission, energetic electron emission, was attributed to muon decay rather than beta decay. However, a muon could form in a chemical environment. It is hard to understand. So basically, he's basically saying, I don't believe that the muons that are being claimed to be observed by HOMLID are real, and it's actually an energetic electron. Okay, first, a single assumption can be used to explain several independent behaviors, which leads to the conclusion that quadrium results from the fusion of D. The logic starts with the observation of the formation of tritium, when both deuterium and hydrogen are present. So basically he's saying, follow the logic, and this is the logic I used when I was showing the initial reaction tables built by Philip Power and Brian, the latest version. Okay, so... the logic starts with the observation of tritium when both deuterium and hydrogen are present. The formation of tritium can be explained by the capture of an electron during the fusion process. And as I've said over here, electron capture is a weak interaction process. Parkhomov tables help here. And then if we go to pages 32 and 33 in Matsumoto's book, we will have also a piece of the discussion point here. So I need to go here, and I'm going to go to 32 and 33. And this is, okay, not in this paper, in the other paper, 32 to 33. Here we go. 32. So ordinary water, this is what he's talking about, but in Matsumoto's terms it will occur like this. The hydrogen in our 3 hydrogen nuclei situation with 2 hydrogen and an electron produces 2 helium, or it produces a deuteron here with a proton, and then this comes together and produces 2 helium and so on, and we end up by producing 3 hydrogen plus an extra hydrogen goes to form a Triton. Okay, so we know 3 hydrogen exists. Tritium is formed, therefore. So this is the kind of thing that's proposed by Matsumoto. Okay, let me go back here. Yeah. Okay, so I am asking today to have a serious conversation with Dr. Edmund Storms to understand how his theory is not explained by Matsumoto's proposals. Because everything he's doing is working from the quadrium and quadrium ion onwards. And he's trying to explain the difference in energies without that initial step that would also produce a quad neutron. The quad neutron we're going to show experimental evidence for the existence of, as determined by Matsumoto in a little while. It's more likely, in my view, for what it's worth, that a fully neutral structure can exit metal, go through the electrolyte, go through the glass, and interact with nuclear emulsions than the quadrium coming out. Because the quadrium is still a hydrogen isotope that can't travel very far in water, it can't travel through glass, it can't travel through air, it can't travel through the emulsion package. Not going to happen, ain't going to happen, not going to happen, right? It can produce helium outside, which is where the story stops for Dr. Edmund Storms, but I don't think it can produce the observations that you will see in a little while that were produced in the early 1990s, okay? So there has to be this previous step to get to there, okay? All right. So, so he's making the single assumption here. Basically, if you can form tritium via weak interaction, then why can't you form quadrium? And this is the same logic that beryllium used. This deuterium can then accumulate and result in DD fusion with the production of quadrium, even when only normal hydrogen is initially present. That's what I showed you in the work of Matsumoto. As a result, the use of normal hydrogen is expected to exhibit the same behavior as pure deuterium, but with significantly less quadrium produced, when this is all consistent with Matsumoto, with much smaller energy, along with production of tritium and deuterium. Yep, okay. Why? And these gases were observed in palladium deuterium experiments, electrolytic experiments by Matsumoto. Okay, and I've shown you that data in the past. It's in the book. Why this electron capture occurs will be the subject of a future paper. Why indeed? Why indeed does the electron capture occur? Why does the electron capture occur? And that will be a subject of a future paper. Matsumoto says something compresses it into a small spot. That's the point of electronuclear collapse, and all of that matter does stuff which looks like it's doing some electron capture because you're getting these quad and di-neutron things coming out, and he actually says full matter collapse and rebirth. Okay, that's the end of his story. In Ken Shoulders, he's saying that there's a solid vacuum object which is a multiple toroidal structure, causes matter to go into a quark soup. It is like ball lightning, like Matsumoto is saying, and then it comes out and it's very efficiently transmuted. Why does it occur? Well, in both cases, it's electron clusters. And we now have Dr. Edmund Storms talking about a future paper. Okay, please, Dr. Edmund Storms, publish that paper quick, right? Future paper where, as per his ICCF 26, following on for his statement that I think Ken Shoulders has probably got something there. In ICCF 26, he's saying electron clusters is what does it, and Ken Shoulders has an answer, right? Maybe that's something's like going on there, and maybe, I don't know, watch this space. Second, the formation of quadrium can account for why all of the helium produced by DD fusion is not trapped in the palladium deuterium lattice. So basically, they're saying helium will be trapped in the lattice. Similar arguments are said in Matsumoto's book, and so it can't happen. So he's saying that it diffuses out, says, which is a well-known characteristic of helium atoms. Instead, the initial formation of quadrium, which behaves chemically like hydrogen, would allow some of this nuclear product to rapidly diffuse out of the palladium deuteride. The observed 4 helium is then formed by beta decay after most of the quadrium has escaped into the surroundings. Yes, Dr. Storms, this is explained as long as you don't see any data, occurring outside of the solution, outside of the glassware, through the air, through packaging of an emulsion and on a nuclear emulsion. It's valid as long as you don't see that. Okay, what's my note here? And I just say, I repeat here to myself that this is even more true for quad neutrons, okay, because they can definitely get out there quite quickly, especially if they're coming out with a sensible amount of energy. And they are coming out with a sensible amount of energy if you're referring to Matsumoto's work. Why? Well, because there's actually a reaction going on where they can be kicked away from. So if we go back to our papers that we were looking at here, where are we? Here. Okay, not that one. Next one. If we are doing a nuclear reaction, maybe it's this one. What am I doing? No, next one. Next one. Have I got too far? I've gone too far. Okay, so here, because of this reaction, here 2D plus 2E plus D goes to 4N, a quad neutron. This is pushed away from these two products. So the deuteron, it kicks off and goes and does the adding of a proton and a neutron to local material, and this high energy neutron cluster then shoots out of the reaction zone. Okay, so you both get your transmutation at the point of fusion, hydrogen isotope catalyzed fusion, and you also get the neutrons coming out as quad neutron to then decay and ultimately produce your helium isotopes. Okay, all right, giving the game away there. Right. Okay. Thus, Storms and Scanlan measured the behavior of the ion emission resulting from the fusion reaction as it passed through absorbers. This behavior, when compared to known behavior of energetic hydrogen and helium radiation, indicated the emission of an isotope of hydrogen, not helium. This emission is assumed to be so basically he's using a hydrogen absorber. Actually, palladium is one of those things, but also titanium might be a hydrogen absorber. Anything that absorbs hydrogen, basically. Palladium's the best, but anyway. So the emission is assumed to be for a quadrium plus. So, but that's okay, because if it doesn't matter whether Matsumoto was right or completely right, or Edmund Storms at this point. It matters when you are looking a long way away from the source of the reaction. Okay? As noted above, the fusion product would be expected to be the result when either D or H is present as the fusion site, because the fusion of HH would produce D as described above, as I open this up. Fourth, transmutation reactions involving the addition of deuterons to produce elements that were not previously present in the material add further evidence supporting the formation of quadrium, okay, which is the main focus of this paper. So he's saying that if we see transmutation that is based on deuterons, it is supporting quadrium. And I would argue that it doesn't discount this, because yes, quadrium is produced, but the deuterons aren't necessarily coming from a specific interaction of quadrium with the surrounding isotopes. It's with this deuteron, and then the quadrium comes out. Okay? All right? I hope that's clear. For a transmutation reaction to occur, 3 conditions must be met. First, the fusion product must have enough kinetic energy to overcome the Coulomb barrier between it and the target, when the reaction probability being sensitive to the kinetic energy and the charge on the target nucleus as determined by the atomic number. Second, the resulting nuclear reaction must be exothermic. So all of these are the basis for the Parkhomov reaction tables. All of them. That is the basis on which those reactions are calculated. Finally, something else must have been emitted in the opposite direction. What you mean like these things? These things being emitted in the opposite direction? Why? This gives you the explanation here. To conserve momentum when the resulting mass energy is dissipated. The creation of many observed transmutation products with the emission of neutrons is consistent with these requirements when quadrium is the fusion product as described next. Again, this does not discount Matsumoto's theory. This must be addressed with Dr. Edmund Storms. The quadrium plus appears to be emitted with a series of unique energies shown in figure 2 and 3, some of which might have enough kinetic energy to overcome the Coulomb barrier at an observable rate. The resulting transmutation reaction is exothermic as noted below, and proposed reaction emits neutrons as required, second nuclear product. Thus, all of the requirements have been satisfied. Furthermore, a series of transmutation products can be expected to form as the fusion product reacts with the elements formed by the previous transmutation reaction, thereby adding 2 additional neutrons to the target as observed and described below. So this is what you call nuclear burning. This is what Matsumoto calls nuclear burning. And this here is exactly the point that I made to the EU team. They need to deeply study the target. Let's see what it says here. Thus, all of the requirements have been set. Furthermore, a series of transmutation products can be expected to form as the fusion products react with the elements formed by the previous transmutation reaction, thereby adding. So, okay, so it occurs near where the reaction occurs. Because these reactions occur at a low rate, this kind of concentration of the resulting elements and isotopes will depend on how long the fusion process has occurred and its rate. The decay of the resulting radioactive nuclei would create additional uncertainty. These variables frequently uncontrolled and not even acknowledged. Not even acknowledged? People don't acknowledge these things. You mean that they deny they're a real thing? No. Oh dear, that's just crashed. You got to love it, haven't you? No. What, really? Okay, no, it's not. It's finally done it. Making the results difficult to compare. Further difficulty is created because fusion occurs only in certain isolated... Look at this. Further difficulty is created because fusion occurs only in certain isolated locations with only nuclei very near the fusion site being transmuted. Thus, the examined location and the duration of the study will both determine the observed result. What did I ask the team at Stitch-In to do? To deeply study their target materials after a sufficient time of exposure to the deuterium being. You need to run it for long enough so that there is enough potential reactions to be observable in the small areas in which they will actually occur. Okay? All right. This would, from Dr. Edwin Storms to Konrad Chersky, pay attention. You know, just because you don't look and you don't run your samples for long enough does not mean there isn't something to find. Okay? And to increase the likelihood that you're going to find transmutation products, which is not, I agree, what you want to find, but to increase the likelihood that you will be able to prove and not be able to falsify your hypothesis, you need to run it for long enough and study deep enough. As an example, figure 4 summarizes a collection of elements measured throughout a thin layer of palladium deposited on plastic or glass beads subjected to electrolysis in D2O as reported by Miley. Looks like the Patterson cell, something like that. Mainly, many other, except that was something like the Patterson cell. Many other studies show a similar relationship between the amount and kind of transmutation products. Yes, they do. Many other studies show similar relationship between amount and kind of transmutation products. with the formation of many similar elements being favoured. Yes, this is true. This is what happens. Of course, some of these elements might be normal impurities in the material, and some transmutation products might be produced by unexpected impurities. Nevertheless, this study provides a useful example of typical behaviour with 4 different regions being identified. These regions are proposed to result from the presence of certain target elements having sufficiently high concentration for the transmutation products to be detected. Okay, so he's trying to justify this for region C here, which is around palladium. This is the most plausible one here. Region C is proposed to result from the reaction between quadrium and palladium with additional elements. We could go to the reaction calculators and work this. We might be able to do that. We can do that. I might not do it now, but I did it earlier, and yeah, it kind of produces those elements. Being formed as quadrium reacts with the resulting transmutation products. Okay, so what's he saying? Let's do it anyway. So we've got palladium here. So let's go back to our thing here. Did we actually have it up here? Let me see if I can find it still. Did we? LENR Academy, there we go. All right, okay. So let's do this live and on air. We're going to get rid of all of these, clear all and clear all. We are looking at fusion reactions. So we are going to say that our, what have we got? Well, we don't have quadrium, but we do have deuterium, which is what they're talking about. And we have palladium. And what do we get? Well, we get silver and cadmium. Okay? We need to turn that off. What is it doing here? Okay. Again, it's remembering from something before. I don't know. There we go. So palladium comes to cadmium, and then we come down here and we got silver 107. What have we got in here in terms of isotopes? So I've turned that off. Oh, it's doing it again. Okay, turn that off. Deuterium. Is it what am I on here? Okay, deuterium. Turn that off. Okay. Okay, all right, here we go. So when we look down here, there's only one isotope of silver here, and it's Ag107. There's no other isotopes of silver. This is very important, and this will be part of the discussion. So you go down here. I've got someone wailing downstairs. I don't know whether you can hear it. Okay. So that's he goes into a discussion on the silver down here. So Biberian, that's John Paul Biberian et al., studied the transmutation of palladium to silver using a palladium cathode in an electrolytic cell containing deuterium oxide. They found the stable Ag107 to be present in greater abundance than other stable isotope Ag109, but only in certain locations that had become abnormally hot. Okay, so as I'm saying, there is no way that you can get from deuterium to 109 as readily as you can get to 107. Why is that? Well, it's produced from palladium 105. What are the isotopes of palladium? If we go to show element data and we click on palladium here, what have we got? We've got 105. Okay, so and that one is where have we got it here? Where's the relative abundance? See, I know where this is on Philip Power's version. Atomic weight, electron valency, atomic number. Where's the relative abundance here? Okay, I'm going to go here because I know where to find it. Show element data. Palladium. PD. Not there. Palladium. There we go. So 105 is a relative abundance of 22.23. So we add a deuteron to that, we get to 107. But 107 basically doesn't exist, does it? So hence you might get more 109. You get it? You get it? So it changes the isotopic ratio. We go back to fusion reactions over here. Does it remember it? Okay, fine. So we have our, if we go to silver, there's only that silver isotope. Yeah, there's only that silver isotope, and that's from palladium 105. Okay. Whereas if we go back to our silver here, you can see that the ratio should be, it's nearly 50-50, okay, to 109. But there's no real way to get there with deuterons. Okay, so deuterium is fusing, but that, of course, does not discount the work of this, which says that high energy deuteron is coming out at the point of reaction. At the point of reaction. Okay? So that's the initial reaction that produces quadrium. So it's entirely consistent with the theory of Takaaki Matsumoto. The transmutation reaction, oh, I'm going to go back up. So we've explained the key element observation here, where palladium is moved to silver and the different isotope is shifted to 107. Okay. I remember actually in an ICCF in Boulder, Colorado, when Mike McCoubry was talking about this, I literally worked out real time using the LENR Academy, using nanosoft.co.nz, why this ratio has occurred as he was speaking. He mentioned it and I worked it out almost immediately. And so, yeah, this is a very well-known observation in the field. The next, so this reaction described in detail in the next section, we've dealt with that. Region D results from the reaction between quadrium and platinum impurity. So you can see that whereas the platinum's there, and so you've gone up to here. So let's just do that. Why not, since we are here? Let's do it in the LENR Academy version. We'll change this to not that, but we'll change it to platinum. What do we get? We get the formation of, I don't know why I've got silver in there. Why have I got silver in there? Okay. Oh, because it's got plate. It's remembering that. Okay. So it goes to mercury and gold. Hey! Oh, that's only if we got radioactive platinum. Okay. Oh, no, reduces that. And okay, the final output. Okay, right. So there we go. So we start with something very, very expensive and we end up with something less expensive. Okay. Maybe. So but we can get mercury out of it. Okay. And that is what appears to be observed. So we're good on the C and D sections here so far. It doesn't explain, because this is just fusion, it doesn't explain why we get the lighter elements here, the lighter elements. But it does explain why you're moving in this direction. Okay, so good, good, good. The regions A and B are proposed. Okay, so this is not so good an argument here, to result from the reaction between quadrium and other impurity atoms. He's relying on impurity atoms here and their transmutation products in the active material, not as the result of the fission of a transmutation product as commonly believed. For example, the magnesium might instead result from the transmutation of sodium and zinc from the transmutation of copper. Well, we saw zinc being transmuted from copper in the plasmatron and magnetohydrodynamic compression device of Klimov the week before last. And there is a new paper out where they observe the form. They actually quote the paper by myself and Benjamin Huang et al. As a reference, and they actually use sodium electrolyte in electrolysis, and they produce magnesium. Okay, so they are quoting this type of reaction. But the real problem here is, where does iron come from? Because iron is observed in almost every experiment. Now, we have a reason why iron is observed, and also nickel. So if you look at the controlled nuclear synthesis patent 2003 of S. Vyachemenko, he shows two things. One, an iron-rich crenellated, but it's not so good, perfect, because it's produced in an explosive electro discharge compression process, which does the magnetohydrodynamics, although he doesn't mention magnetohydrodynamics once in the entire book, although he does refer to 2 papers that talk about magnetohydrodynamics. Anyway, in that whole 760-page book or whatever it is, but he sees iron, and that is his one SEM that he chose from thousands and thousands of sequentially functioning nuclear transmutation experiments. He chose the iron. And then he also shows some elemental analysis where he shows isotopes of nickel all being transmuted to nickel-62. Why is that important? Because iron is, across all of the isotopes of iron, it is the highest binding energy per nucleon of all of the elements in the periodic table. But nickel-62 has a higher binding energy than any isotope of any element in the periodic table. Okay? Hydrogen has no binding energy. That's protium. It has no other nucleons. Protium's a bit special like that. But in the case of nickel-62, it is the most the highest binding energy of any element isotope. And that, I believe, is why he chose iron as a spherical structure with a hollow structure in his patent in 2003. And he chose nickel, the reaction that occurs with nickel, to show that it produced the highest binding energy nucleus. It shifted the isotope ratio, which is heavily skewed to the lighter, lower binding energy isotope element. So if I go and go back to our thing we had up here a minute ago, if we go to the show element data here, and we go to iron 26. Okay. Binding energy per nucleon here. Okay, so we can see that iron 56 here, iron 56 has 8.77055, and you can see the average is quite high here. But if we go to nickel here, and we look at nickel 62, 8.794329 binding energy per nucleon. Okay, so back to iron, 7943, this is 792. So there we go, the binding energy of nickel 62, and so that was very, very important. Okay. All right. So ultimately, if you are in a really compressive situation, you're going to get a lot more nickel out of the situation than you are going to get iron. And I think this is why meteoritic iron or meteoritic metal, that's nickel and iron, tend to be very, very special metals. Okay? Very, very special metals. Okay, so I don't believe his argument works for this zone B. I believe that a magnetohydrodynamic structure with a fractal structure that produces a ball lightning structure, which is essentially what Ken Shoulders got to and what Matsumoto got to and what was sent in 1995 as the means by which fusion occurs to Dr. Edmund Storms, produces iron. And in, I think it's the Miley report from 2008-9, iron was the most observed element synthesized regardless of what experiment they were doing. Okay. And you've heard me talk about that ad infinitum. So the argument starts to break down when he's referring to A and B, and I'd like a long and deep discussion with Dr. Edmund Storms about that. If you're listening, Dr. Edmund Storms, I'd like a discussion about that, why that is, and to look at the other physical evidence that isn't just, you know, data abstracted from what is physically observable. So we talked about the 107 there, in greater abundance than any other stable isotope than the other stable isotope of 109, but only in certain locations that had become abnormally hot. So this is very consistent with the synthesis process going on, particularly of that claimed by Matsumoto. The transmutation reaction apparently occurred near the surface in only certain locations, with mainly one stable isotope of silver being the result. They proposed that palladium fused with deuterium, but did not identify how the momentum could be conserved when the resulting energy was dissipated. Right, yeah, so how could it be? Dash and Wang observed that the presence of silver on the palladium cathode after electrolysis using light water. This material hinged its shape over time. This material changed its shape over time, suggesting that it contained radioactive isotopes. Silver production, then neutron emission with a range of neutron energies measured below 3.5 MeV. These studies provide a good test for the proposed mechanism. This is interesting, actually. This is where the argument's a bit stronger on the part of Edmund Storms. These studies provide a good test example for the proposed mechanism. In order to get silver to form, one proton needs to be added to palladium nucleus. This cannot happen if the fusion product is 4 helium. On the other hand, the behavior can be fully explained if a quadrium is emitted, as Storm suggested. The reaction then becomes this and that to that, right? So he's making this whole reaction to account for the data, and that's okay. Table 1 summarizes the resulting nuclear products. Ag107 results as the first stable product with smaller amount of stable 109 being produced as secondary product that would increase as the cadmium 109 decays. Okay. All right, so he's proposing this reaction. Notice the positrons, beta emission, and the resulting annihilation gamma ray would be expected as well as X-rays. Notice that the positrons, beta emission, and resulting annihilation. So if you see positrons emitting, that's not necessarily that your deuterons are doing a deuteron-deuteron reaction and doing internal pair creation, internal pair production to produce a positron and electron. It's not necessarily saying that, because you can get positrons from other places here, positron, okay, in the case of palladium. However, the transmutation rate is too small to add, so because many studies are made with palladium in the material, a similar series of nuclear reactions should happen during all such studies, regardless of which isotope of hydrogen is used. However, the transmutation rate is too small to add detectable energy to that produced by fusion reaction itself. So what they're saying is the transmutation reactions don't significantly add to the actual energy that's yielded. It's the primary hydrogen energy reactions, nuclear interactions that produce the energy, and that is exactly as per Matsumoto. They're not in a disagreement there. In summary, the calculated isotope distribution of silver in Table 1 is consistent with the observations of Barbarian et al. The presence of silver with radioactive isotopes is consistent with the observations of Dash and Wang, which would be true as explained above, even when light water is used, as was the case. Okay. Consequently, the neutron spectrum can exhibit a broad range of values. Okay, so in this particular, in figure 2, where is it? Figure 2? Oh, it's a long way up. Okay, anyway. This is a reasonably good argument about the neutron energies, but there will be a range of neutron energies emitted in both scenarios. So this is actually quite a good argument. He's saying that as the energy of the quadrium increases, then you get to a point where all of the reactions produce transmutation. So the best fit between calculated and measured values achieving a mass of this. Using this mass, the resulting energy for release of other transmutation reactions can be calculated. This mass indicates an energy release of 14.2 million electron volts when quadrium decays by beta emission. So he's saying that the quadrium decays by beta emission to produce 4 helium, as was in Matsumoto's work. Consequently, more than half of the heat energy measured during the formation of 4 helium might be attributed to the beta decay of quadrium. Some of this energy may not be measured as heat energy, as the expected emission of an antineutrino would carry away some kinetic energy. So you're going to lose some energy there. This expectation necessitates that measurements of energy and helium resulting from fusion be conducted with greater precision in order to properly understand this reaction and the resulting helium energy ratio. Okay, so in this case it's saying that the fraction of the energy emitted from quadrium that reacts with palladium to cause the formation of silver as a function of quadrium energy. So as the quadrium energy increases, more and more of the interactive palladium will transmute, And when you get above a certain threshold, then 100% of them will transmute the palladium that it interacts with. So this is the reaction that we talked about at the beginning. This reaction is proposed to be one of several sources of the low level neutron emission that is occasionally reported. Okay, so he's saying that this neutron here is where you get the interaction of the quadrium with the material or that's otherwise in the reactor, and you get some neutrons coming out. But again, that kind of thing is still there in here because you can still have this doing the reaction, and also that you can have the quadrium produced with the neutrons here. Okay, so there's nothing really that favors one or the other currently as we are in this argument this evening. We're going to get on to an interesting argument. As I say here, same for Matsumoto theory. You can't see that because it's so small. Because the resulting nuclear products remains at the fusion site, repeated reactions involving quadrium can result in a series of transmutation products or their radioactive decay products. As a result, a series of new elements with many deuterons being added to the final product should be observed. When radioactive elements are produced, various kinds of radiation, including gamma rays, electrons resulting from beta decay, and positrons with the annihilation radiation can be expected. Okay, positron and annihilation radiation. Here, this is what could be expected, okay, when you have these processes going on. Because the resulting isotopic abundance will not be normal, the correct identification of the element can be challenging when a mass spectrometer is used. Right, so normally, some mass spectrometers identify elements based on the mass ratios, based on what it should normally be there in nature. Because there are some isotopes around palladium that have the same rough mass, but they're actually a different element, you can end up by misidentifying the elements using mass spectrometry, and this deeply complicates the process. So you kind of need to do multiple different types of analysis in order to determine what's going on. Spectral analysis, optical spectral analysis, EDS, ICP-MS, all these kind of things going on. Okay, otherwise you might identify the wrong elements. But of course, as I note here, if you are someone that doesn't want to see any transmutation, you don't have to worry about all of these problems because you're not going to look. Formation of transmutation products. Right, now in the next series, it's not necessary to go into here because he's just going through the data, of which there is plenty, where there are transmutations that are involving the multiple addition of deuterium D. Okay, so you've got the Iramura experiments, cesium to praseodymium, strontium to molybdenum, barium to samarium, barium to samarium, calcium to titanium, tungsten to osmium, tungsten to platinum. Okay, so all of these things are well known in the field, but that does not discount the fact that Matsumoto would produce it using this particular proposal. Okay. And then it's on and on and on, lots and lots of data. However, the increased nuclear charge on the target would be, okay, that's just an explanation from why you wouldn't get certain things. Strontium, okay, so this is just lots and lots of different experimental data. This is good support for his theory, but unfortunately it doesn't actually discriminate between his concept and that of Takaaki Matsumoto. Okay. Repeated transmutation would cause the accumulation of 9 beryllium, 11 boron, and 13 carbon with additional neutron emission resulting from each reaction. Because these elements have a lower nuclear charge than palladium, the transmutation reaction is expected to occur with greater probability when the lower Ng quadrium encounters a lithium nucleus. This is if you are using lithium. Again, it is not excluding Matsumoto's theory. As a result, the material will become radioactive. Okay, so these are some things before we go on to the additional data from Matsumoto that need to be considered that he's warning about here. So the transmutation mechanism is so inefficient that only a small fraction of the emitted quadrium will encounter a nucleus before losing its kinetic energy. However, when the fusion rate is increased enough to generate practical power, i.e. if it's actually working and doing what you want to do rather than being just a statistical interesting anomaly, These transmutation reactions will occur at significant rate, and this is what Matsumoto calls nuclear burning, which you could put to good use. But anyway, as a result, the material will become radioactive and undergo modifications as created elements accumulate near the nuclear active environment. I respectfully, Dr. Edmund Storms, disagree. If this is packaging, if the reaction gets so big that it's packaging it into these magnetohydrodynamic structures that take on a life of their own, can exist for 2 days without further stimulation or feeding, but can be fed to keep the process going, particularly in a cavitation system, then it tends to produce stable elements, particularly if you've got an abundance of light elements in play. Okay, it doesn't like to produce radioactive elements. In fact, it'll take radioactive elements and make them stable. Now, that's what I was going to talk about this weekend. Unfortunately, this paper was released and it follows nicely on. And because I'm working on Matsumoto's book in the final stages of getting the PDFs out to you guys that have booked that through the Kickstarter, it's really relevant to compare the latest thinking of one of the most senior researchers in the field with the early thinking of Matsumoto. Okay, so I argue that yes, if you overdrive this process, you might get radioactive elements, and also if you start with, as he's suggesting here, uranium-238, which is not fissile uranium, you could produce the production of polonium-242 and other trans-uranium elements. This might be a concern, right? These kind of things. Okay. Additionally, neutron, positron, electron and photon radiation will be emitted at rates that would justify shielding. These consequences will require the generator to be shielded and the nuclear active material to be replaced periodically. The use of light hydrogen is expected to produce tritium. These predictions need to be considered when practical energy generator is designed. Yes, with light hydrogen, I do think we're going to produce tritium. That is the evidence. That I think is very clear. Thomas Claytor, I stood next to him as he got the Preparator Award in Constigliani di Asti for proving that tritium is produced. And he worked also at Los Alamos National Laboratory in a corona discharge. So yes, you will produce tritium with light hydrogen, but you will, under both theories, get neutron, positron, and photon radiation electrons. So this is beta particles, this is positrons, this is X-rays and gamma rays. And yes, these will be coming out unless it's in a little package structure that does all of the work in there, and it's got this Borg on the outside that prevents this radiation coming out. And it's only when you break these things up that you get a little dose of radiation. If you keep making and breaking early, then maybe you don't get any serious radiation. If you make them and break them, you're going to get some things going on, okay? But I believe for the majority of the reaction, when it's in the coherent matter state, when it's doing the coherent energy transformations, it won't be releasing these things. It will be if you're smacking it with a hammer, right? If you're doing firing a deuteron in, it's more kinetic. It's more kinetic than working with the way that nature wants to work. He actually argues also in here that biological reactions can occur. I think we might get onto that. Conclusions. The proposed emission of quadrium as a result of low energy fusion of deuterium can account, it might not be the way it works, but it can account for the reported transmutation products, and so would, of course, this. This would also, because it produces quadrium as well, it would, can account for reported transmutation products, as well as identifying the source of the reported neutron emission. Transmutation can be explained without any additional assumptions being made, while the required exothermic behavior and conservation of momentum are satisfied. The proposed mechanism can be described as what we said before. It'll add a deuterium nucleus and throw out 2 neutrons. All nuclei located close to the site of the fusion reaction can be expected to transmute to other elements as fusion of the hydrogen isotopes take place. This secondary reaction cannot be avoided and would result in weak neutron emission, which is detected when suitable measurements are made. The transmutation products formed by the energetic D or T emitted when H fuses have yet to be fully explored. This reaction is proposed to result in the nuclear products found created in living systems. There we go, in living systems. Now, I'm not so sure, but anyway, this reaction is proposed to result in the nuclear products found created in living systems, which with the required nuclear active environment being created in the living cell. This is very interesting. Now, I'm very much looking forward to his follow-on paper and for him to talk about this. 52 and 53 is this. This might be work of. Yes, John Paul Barbarian, Biological Transmutations. He's accepting that this must happen. And there's no particle accelerator in the traditional sense in a biological cell. But I would suggest that nature likes to work through coherence, gently bringing these things together. Okay? Where were we? A new value, this mass here, for the mass of quadrium is calculated based on the measured neutron energy when palladium is transmuted to produce isotopes of silver. The use of this value would make the decomposition of quadrium into tritium and neutron endothermic. Okay? So this might not occur. Because of this mass, you wouldn't get enough energy out of the decay into tritium. And similar arguments are made by Matsumoto. Okay? Okay. Hence, it's hence not spontaneous. In other words, the observed formation of silver is in direct conflict with the claimed behavior resulting when quadrium is produced by the application of high energy from tritium and deuterium-tritium transfer reactions. So this paragraph I want to spend more time thinking about. I think this is a good argument for his case, but it ignores the data which I'm about to show you. This ignores the data that I'm about to show you, which really is, it needs to be considered. Use of the mass to calculate the energy resulting of the fusion of deuterons reveals that most of the resulting energy is released when quadrium forms helium, 4 helium by beta decay. This may explain why the kinetic energy of the emitted nuclear products measured by, what's his name? He's up at the top here anyway. He's in, what's his name? Caribou. I got to there before I got it here. Caribou. I got before my memory's not dying as quick as I thought. Okay, good. Right, Caribou. And Storms and Scanlan is Caribou et al. And Storms and Scanlan is so small compared to the energy released by fusion reaction. This also reduces the amount of momentum and kinetic energy required of the accompanying electron emission after fusion has occurred. So yeah, he's trying to discount the amount of energy of the electron, because if you have the very fast electron coming out, you're going to get Bremsstrahlung radiation. And Bremsstrahlung radiation, if you don't see it at the energy that would be expected, you need to explain that away. Okay. So, the emission of quadrium as a fusion product reveals important information about the nature of the fusion reaction. In addition, the implications have a direct consequence to predicting how a practical source of energy would behave. This behavior includes the production of useful elements and the need to protect the environment from the emission of dangerous radiation as the fusion and transmutation rates are increased to industrial levels. Okay, this is still thinking about the problem as a 2 or 3 body problem, not thinking of it as being inside a magnetohydrodynamic structure. Now, what was I intimating to multiple times in this presentation? Well, I'm going to have to go and dig up the later version, the updated version, because it's got better imagery in it for you. That's going to be in the book, which I hope to get to you all as a PDF version for final look-see for everyone before it goes to print later. And that is the paper that was submitted September the 13th, 1990. September the 13th, 1990, and published February the 8th, 1991. and that is observation of quad neutrons and gravity decay during cold fusion. Okay, so we're going to pull up the later version of this. Okay, so that is 116 is down here. Is it? Okay. So this is the new version for the book. Okay. The Nattoh model predicts that neutron nuclei such as quad neutrons are produced. So they call it neutron nuclei, and he gives you can see the difference between multiple neutrons and neutron nuclei. And so, like, to give you an example of what I'm talking about, this is 2 neutrons, this is a quad neutron nuclei. Okay? 2 neutrons, quad neutron nuclei. Okay, so that's kind of the separation between the two. As a result of the emission of a new particle, the iton, several quad neutron decays have been successfully recorded on nuclear emulsions. Oh my God. Oh my God. This means that it has come out of the metal, through the electrolyte, through the glassware, through the air, through the packaging of the emulsions, and into the emulsions to deposit the decay products. This is not something that would be possible with a quadrium and a helium. Just wouldn't happen, right? So what you're going to see here is the unique experience of Dr. Takaaki Matsumoto, which is devoid. There just is nothing like this in the rest of the field. Nothing like it. And I don't think there's almost anyone studying nuclear science on planet Earth right now that had the level of expertise of this consummate nuclear professional. Okay? Many strange phenomena have been reported in connection with cold fusion experiments, such as a very wide range of neutron emission. Okay, we've been talking about that. Extremely small ratios of neutrons compared to heat and tritium production, and very fast decay of activity. Yes? Therefore, it has been accepted that cold fusion cannot be explained by conventional theory. The Nattoh model predicts a new fusion reaction in which hydrogen atoms assume the role of catalysts. We talked about how that works earlier, based on the H3+ ion. Okay, which is one of the most abundant ions in the universe. Okay, they assume in which hydrogen atoms assume the role of catalyst, intra and interclusters of hydrogen atoms. The latter causes hydrogen chain reactions that are similar to the neutron chain reactions in a fission reactor. On the other hand, the intra-cluster hydrogen catalyzed fusion reaction, the emission of a new particle, the iton, is predicted. Reference 5 reported that itons were successfully observed on nuclear emulsions during cold fusion. As a result, we have concluded that that strange fusion products, such as quad neutrons, should be produced after the emission of itons as follows. So, you can have deuterium plus an electron plus the catalyzing deuteron goes to quadrium plus a positron electron bound together with a neutrino and a deuterium nucleus, the D. This is what I'm arguing that in this model produces all of the evidence that is claimed by Storms in his latest paper. For the emission of a single iton, I1, and for this is dual, the same input plus you've got 2 electrons in this case goes to quadrium and an iton and 2 neutrons, or it goes to a quad neutron nuclei, okay, plus the 2 itons and a deuterium nuclei, okay. All right, among the fusion products, quadrium cannot be released from the cell. Very, very important thing here. It cannot be released from the cell. Yes, it might be able to come out, it might be able to decay into 4-helium, whatever. Quadrium cannot come out of the cell. It can't do that. However, neutron nuclei such as quad neutrons could escape from the cell to decay in nuclear emulsions if they have sufficiently long half-lives. This is a necessity, right? In this technical note, the nuclear emulsions used in reference 5 are carefully re-examined. So he's learning from what I was talking about last week. He's learnt from that, and he's saying, well, you know, basically this must be going on, and therefore we must be able to observe these things in the nuclear emulsions because they must be able to get out. Okay, they were re-examined. So he didn't do any more experiments. He just went and looked harder to search for traces of fusion products. Several quad neutron decays and micro explosions were successfully observed. Searching for the traces. We have successfully searched for nuclear traces produced by fusion products. The nuclear emulsions that were placed outside of the cell were recorded during the previous experiment 5. That experiment was done by electrolyzing heavy water mixed with 3% sodium chloride. The traces on the films were examined by microscopy with a magnifying power of 500 times. I literally have scanned the original negatives and positives that were produced from the photographs that he took with this 500 times magnification here. Okay? Quad neutron decays. We have observed several kinds of traces that are different from those seen previously. So that he's learning in this reanalysis of these type of data that only he produced, he's learnt. For example, figure 1 shows the decay mode of emitting 2 neutrons as follows. So a quad neutron decays to 2 neutrons, 2 helium. The 2 helium then decays into 2 protons, and the 2 helium will, the quad neutron will also produce 2 electrons and 2 antineutrinos. Now you will not see the antineutrinos. You should not see the neutrons, but you should, you should not see these quad neutrons as it's entering in, but you should definitely see the neutrons, the helium here, the electrons, and the 2 protons. Okay, so the assignment of particles in figure 2, in this mode, 2 protons are simultaneously produced by the decay of 2 helium, while the 2 neutrons can recoil to 2 protons. Okay. However, these are probabilistic processes, and the 2 additional protons are not always produced. Fortunately, 4 protons are produced by chance in figure 1. The microscopy is well focused on point A, and thus the traces of the recoil protons at point E and G seem to be broader. We have also observed several traces caused by only the decay of 2 helium. Okay, right. So let's have a look at this first one. And what's happened there? my better imagery has epically failed. I don't know what's happened there. Let me go and recompile this. Epic failure. Let me go and recompile that. I don't know. This might be the joy of this might be the joy of how should we put this? Acrobat failing. If you see those images in the book, sorry. No, there won't be. Epic fail. Oh dear. Okay, let me go here. And that was, what are we looking at? Okay. Let's see if it's got it right here. Yes, that's what I'm expecting. That's what I'm expecting. Right, let's see if we can get it right this time. I'm going to republish that. I'm going to publish it into there, why not? Be with you back in a second. Sorry about that. That was not the best time for that to happen. Has he got it right? Yes, that's better. Okay. All right. So what are we looking at here? Okay. This is the thing. So he's saying that this is focused on what does he say? Point A. Where is point A? Point A. That's D. That's C. That's F. That's E. That's A. Okay. So it's focused on point A. So he's focusing on point A. That's this point here. Okay. He's focusing on point A. Now, when you get focused, you'll get a straight line. Okay. So what are we seeing? We're seeing a hard straight line here breaking up into two structures. This is not going for very long, so it's probably a heavier particle than these two. These are able to go away with the energy. This is something over here. This is something over here. What is his reading of this? Well, the quad neutron comes in here to 0.0. This is ground zero for this reaction. A neutron flies off here, and a neutron flies off here. In both cases, they collide with a proton, causing a recoil, because a proton and a neutron are basically the same mass, essentially, all bar the variance in electron and antineutrino. And this is the basis of neutron moderation. When you use something like high density polyethylene, which has a large number, or water, which has a large number of protons in it, the neutron is coming out, it's colliding with the proton in the material, in the nuclear emulsion, and you're seeing the proton go away. The neutron does not observe to interact with material because it's neutral, it's traveling through it, but when it hits the proton and imparts some of its energy to the proton, it then shoots away, and the proton interacts with the radiographic emulsion. So that is happening here and here, okay, producing these two recoil protons. Then what you have left is the 2 helium that comes over here, and it interacts here, and then it breaks up into 2 protons, okay? So let's go and have a look at the reaction going over here. So somewhere here, a quad neutron is coming in, it's breaking up. You have a neutron going over here. This is the recoil proton. You have another one comes over here. This is the recoil proton. Then the 2 helium carries on, and it interacts with the emulsion here, and then it breaks up at this point into 2 proton tracks. This is, in my view, very strong evidence of this particular reaction chain. We know that it cannot be quadrium, it cannot be 4 helium that is exiting the glassware of the experiment. It cannot be. So it's very good argument to say that it's 4 neutrons. That is then breaking up into 2 neutrons, 2 helium, 2 electrons, and 2 new antineutrinos. Okay? And then the 2 helium is going over to interact and produce 2 protons. So you're seeing the 2 neutrons from the breakup of the quad neutron and the 2 helium, and then its subsequent breakup. Okay, very, very compelling evidence. Okay, so then the next one is another trace is the beta decay of the quad neutron shown in figure 4. So this is literally proving the beta decay hypothesis such that it is in isolation of Dr. Edmund Storms. The assignment of the particles as shown in figure 4, we'll look at that in a minute. This can be written as follows. So the quad neutron nucleus is decaying to a quadrium, an electron and an antineutrino, and then the quadrium is decaying to 3 helium, a proton, 2 electrons, and 2 antineutrinos. Now, in each case, you will not see the antineutrinos, and you should not see the 4 neutron nuclei. Hydrogen-4, quadrium, is produced from the decay of quad neutrons as given by equation 4a. 2 electrons caused by the beta decay of quadrium can be observed in figure 3. Okay, so let's have a look at figure 3. So there is the figure. Okay, so this is the event where the quad neutron decays, and that is producing 1, 2, 3, 4, 5 tracks, and this one over here is interacting here. So that gives you an indication of what these various things are. Okay, so what do we have? The quad neutron is coming in here. It decays at this point into quadrium, and then it starts to interact with the emulsion. Okay, I think what he's done is he's focused at this point. Okay, then the quadrium decays. So this is how stable quadrium is. This is how stable between here and here. Between here and here. In this material, quadrium is from point of formation to point of detonation. That is how long it is stable for. Does that allow for the theory of Edmund Storms? I don't know. So at this point, it's then breaking up. It breaks up into a proton and it bends its angle. And that again is a recoil. It's recoiling with something there. The proton is hitting maybe a neutron or another proton, probably a neutron or something. And there's a little bit of an event and it goes off at a different angle. Okay? It's imparting some of its energy to the material. This one is an electron. The electron is coming off at this angle. This one is another electron. Okay? Now the electrons as they're emitted, they don't necessarily have to be emitted with the same energy, and that accounts for what's going on there. And then this little short track here with nothing at the end of it is the 3 helium. Why is that a good indicator of what's going on? Well, because 3 helium is stable. So it'll basically go and stop, right? Whereas in the case of the other one, which produced 2 protons, it's unstable. It goes along, produces a similar type of track, but because it's unstable, it's not a stable nuclei, it breaks up into 2 protons. This is very, very compelling evidence of Matsumoto's theory that quad neutron nuclei are produced. Now, he goes on to why you don't see other kind of products. No electrons from the beta decay of quad neutrons appear. You can't see them because they occur outside, okay? In figure 3, because the quad neutrons decayed outside of this film. Traces suggest other decay mode in which quadrium might decay too. Tritons plus a proton, electron and an antineutrino, triton and a neutron, and 4 helium, electron and antineutrino. They have also been observed. However, these modes are so simple that assignments cannot be made. That is to say that if you have a decay of the quadrium into an electron and an antineutrino, well, all you're going to see is the electron and the helium. So you're going to see a short trace that comes to a stop, very much shortest trace, and an electron. But, you know, how else could that be produced? The triton, again, stable up to a point, and at least stable enough to make the track. And the neutron, well, you might see the neutron from a proton recoiling, but because it's at a distance, you can't really necessarily be sure. And in this case, the proton again will do some action, but you might not see, you don't see the antineutrino. So these are not complicated enough reactions to be certain. Okay, they suggest, but they're not certain. However, he was confident enough to say that this is a quad neutron because this is decaying to quadrium here, the quad neutron nuclei. It then comes in here and blows up, producing a proton and a 3 helium and 2 electrons. Okay, so you can see the whole breakup process there. And in this case, you can see that the quad neutron is coming in, you don't see it, it produces 2 neutrons that produce recoil protons, and then this the remaining balance comes down as helium, and then that breaks up. And this is all logical from the predictions. Okay? And of course, 2 neutrons will cause transmutation, and if you're firing protons at high energy, they might cause transmutation. And clearly at the beginning here, these deuterons, which are part of the primary hydrogen isotope catalyzed fusion, producing quadrium, and with 2 electrons producing quad neutron nucleus, they both produce the deuteriums that would explain all the transmutation products discussed by one Edmund Storms. Okay. He then goes on to talk about quad neutrons microexplosions. This is not really that relevant for this part of the discussion. Here's the beautiful image that was on his 1990 book. And these are different breakup products and microexplosions and his explanation for them. Okay, I'll just read a bit at the conclusion here. I think it's nice. I won't go to everything here. Right. The third question concerns what materials are produced after gravity decay. The inner white ring, no, not that. The fourth question concerns the conservation of matter during cold fusion. The emission of itons causes strange fusion products such as quad neutrons, and the conservation of fusion products is unclear due to cold fusion. The reactions equations 1 and 2 cause most of the heat during production. So what is 1 and 2? What is 1 and 2? 1 and 2 is these. The production of quadrium and the production of quad neutrons and quadrium are the main reactions in cold fusion. Of course, this will decay also to helium. And so this is basically consistent with the claim of Edmund Storms. And the conventional fusion reaction emitting 2.5 MeV neutrons is the secondary process. Again, this is starting to talk of similar kind of justifications as discussed by Edmund Storms. Among the fusion products of equation 1 and 2, almost all the quadrium can be deposited in the cell and decays to tritium, protons, and 4 helium, and so on. Okay? The only thing that is added really here is that if the quadrium is sufficiently low mass because of its formation, which is potential, okay, that then the tritium path is less likely. Okay, but we do know tritium is produced and protons are produced, and we do know 4 helium is produced. So I don't see a lot of 3 helium going on here. Okay, so on the other hand, many of the neutron nuclei, such as quad neutrons, are released from palladium metal to decay outside. Therefore, we cannot satisfy the conservation laws of fusion products only in the palladium metal or cell. So basically, you're losing potentially a lot of energy by these quad neutrons coming out. It is suggested that the concentration of the fusion products could depend on the measuring positions. Okay? So basically, if you're further away from the reaction site, you're going to get different fusion products. From the observations in this technical note, it can be concluded that cold fusion, because of the extremely high pressure of hydrogen atoms, is a small-scale simulation of the events that might take place in the death of stars. While high-temperature fusion takes place on the surface of living stars like the Sun, it is remarkable that gravitational energy as well as fusion energy may now be available. The efficiency of the former is expected to be higher than the latter. So the efficiency of producing gravitational energy is expected to be higher than fusion energy. So what he's suggesting, and by what I showed you earlier here, that gravitational collapse, does he show it in this paper? Yeah, this is gravitational collapse. This is full collapse of matter. It isn't in this paper. It's in maybe the previous one or two. Maybe it's the next one. I think where does he go on about it? Basically goes into a neutrino and antineutrino, which is full gravitational collapse of matter. Where is it? No, it's latter. He's onion slicing his papers, so that the next paper is talking about gravitational collapse, probably. No, it's elements. Anyway, I showed you earlier where he gets the neutrino and antineutrino coming out of the full gravitational collapse of quad neutrons. Okay, so if you have got a gravitational impulse coming out of a phase singularity, then that's propulsion, and that's a lot of propulsion potentially, if you can cause gravity waves, as he's claiming he's observing here. These are apparently gravity waves. These are, in his view, gravity waves and indications of. Okay, so I will take any questions now. Essentially, that was it. I think this is a fantastic paper by Edmund Storms. I think it does a lot to support the early claims of Matsumoto before he realized the larger collective effects going on. And certainly the first time you're going to get any event going on is when you have at least a deuteron in being interacted with in the right environment of compressive state of an additional deuterium nuclei or atomic hydrogen. And so it is hydrogen catalyzed fusion. Hydrogen catalyzed fusion. Fusion between two deuterons catalyzed by an additional hydrogen at least. Can be many, but at least one extra in there to produce something analogous to the H3 plus ion, one of the most abundant ions in the entire universe and principle in interstellar chemistry and so on. So and I think his explanation from a semi-classical point of view is quite nice. It's quite easy to grasp. You can imagine that going on with all those electrons around the metal cluster, the metal grain squeezing in on those things as the electrostatic pressure is pushing it all together. You can kind of imagine that. Where his data is utterly unique compared to all of the other researchers is he's actually looking for particle tracks, which he is an absolute consummate professional in looking for. He's also seeing things which I've gone to in the past, which do not come out of ordinary nuclear reactions. So he can see something unique is going on in these processes because he knows what should be on nuclear emulsions. Okay. Okay, so we're talking about Mario games. That's great. Gary says, would like to see Matsumoto papers on calcium channeling. Yeah, that might be interesting. Yep, stars die. Yep, they have a life cycle. Okay. Okay, I don't know quite what's the discussion, but anyway, you're having a good discussion. That's fine. Okay, I'm going to see if there's anything that looks like a question. Otherwise, I will conclude. So, Old Man builds, in cold fusion they are stable, but in hot fusion they are not. Yes, I'd agree with that. Okay, I will just do a quick overview. Goodbye, Misunderstood. Thank you for joining us. These two presentations, these last 2 weeks, are because I'm deeply looking at Matsumoto's book and I'm looking at latest things out of the field. And you just invites deep comparisons. And in both cases, the work of Matsumoto is extraordinary. It's extraordinary. And it's the difference between people who think of a theory and look for the evidence, and Matsumoto, who had this unique skill in nuclear emulsions, but he read every single other author in the field, line by line. I've got their papers that he printed out all the way up to 2019, for instance, like a full nearly 2 decades after this book was published, right? He was writing and comments and underlining things in everyone else's work, and that is a real that's a person who's dedicated to finding the truth. And I do believe genuinely that is the same with Dr. Edmund Storms. He really does want to find out how this plays out. You know, it's been a good third or more of his life. So you know, basically 1989 to now, you know, it's a long time. So you're saying that these pictures, yeah, so that's a good question actually, Dennis. These pictures have lots of artifacts other than the ones that you discussed. That's a fair point. But I think what he's coming from is like he's experienced in looking at nuclear emulsions. I don't think anyone can argue that like against the fact that these selection of tracks are all coming from the same nucleation point, and you know, this interaction here is likely due to this one. Because after this interaction occurs, whatever did this, it goes out of a different angle. But of course, a nuclear emulsion is an accumulator. It registers many different things that are going on, and so like, yeah, and I thought, well, you know, how can I be sure that all of these things are associated with the same event? Well, it really comes down to understanding that this is a proton track and this is a proton track. And how do you get 2 protons coming out of a point? Well, that would be a decay of 2 helium. Well, where does the 2 helium come from? Well, the 2 helium, that is not a thing that just generally occurs in nature. It just doesn't. It just basically doesn't. 2 helium is 2 protons. That's it. And how do you get 2 protons to stick together? Not easily. Like, go and ask anyone if you can get 2 hydrogen, to stick together, 2 protons to stick together. That isn't going to happen every day of the week. So something must have produced that, and because of the direction here, it points back to somewhere over here. So that is why he goes to make this thing. So you have to point back from the 2 helium to the point of disruption, and then you trace from there to the deflections. Now, the point of disruption of the quad neutron could have been any point along this line, and then you just have to draw a different line for your neutron coming out for your recoil protons here. Okay, and that's it. That is why he's saying that whilst he's satisfied that he found traces suggesting other potential decay modes to tritium, proton, electron, antineutrino, tritium, neutron, and 4 helium plus an electron plus antineutrino. These modes are so simple that assignments cannot be determined, right? So he can't be sure that they are as he can see them, because they could be other things. But I don't believe he's wrong in suggesting this has to be 2 helium, and that doesn't come from anywhere. And I don't think he's wrong in suggesting that this is obviously a stable nuclei, and so this would be your helium. These would be your electrons, and so yeah, and your other 2 thing is you got your proton coming out here, and so that's the only way you can get to this. I think it's a very good point. Okay. No, well, no, it's not a simple photo, Corky. What they're doing is you put the emulsions next to. Well, maybe I'll just go and show you. You can actually have a look. Where is it? Actually, look at the experiment. You can see it in color photos, which I intend to include some. Right, where are we? Up here. Let's find the experiment. So he's using the same experiment in a number of different. Where is it? There? No. Okay, come on. That's when I want the book in my left hand. It's easier to flick through a book. Much easier. Okay, here we go. So it might be something like this, and not that particular one, but did he have somewhere where he shows the emulsions? Not there. Not there. Anyway, he had the emulsions in close proximity. He also observes these, which are cold fusion stars, and so this is an actual whole series of products coming from a point. But the difference between this and the other one is you don't have the secondary branching going on. You just have the overall explosion. And he's got many examples of these. Okay. All right. quadrium Stargate material. Seriously, maybe a metal and a superconductor. Okay. Okay. Right. So I have again increased my respect of one Dr. Edmund Storms. I encourage people who are serious about this field to read this paper, the nature of transmutation and its relationship to low energy fusion of deuterium. And I would encourage all people to read this in context with the work of Takaaki Matsumoto in Steps to the Discovery of Electronuclear Collapse, in which he goes into many of these reactions, and not least he builds upon that. And for me, because the initial fusion energy is partly released in the form of positron and electrons, potentially with an with a neutrino rather, and a deuteron, which is the remainder of the hydrogen isotope that catalyzed the initial fusion. The quadrium comes out with less energy. This is consistent with the claims of Dr. Edmund Storms, and that also with an extra electron in play, you can end up with the production of quad neutron nuclei, and these can come out of the reaction and apparatus all the way from the inside of the metal and electrolyte and glass and air and into the emulsions and produce decay product pathways, which were observed and published in this particular paper. And so, Dr. Edmund Storms, I specifically ask you to answer this in context of your thinking, and bearing in mind that ultimately Matsumoto decided that you are able to get full matter collapse in a structure that involves vast numbers of nuclei, and then it comes out of hollow spheres out of one side, and we know this from the work of Bogdanovich et al. The reason for that is the azimuth through which the magnetohydrodynamic structure ejects stuff from the topological monopole, which they discuss, and we have found in our work, and Matsumoto found in his work, and so forth. So, and in the case of this magnetohydrodynamic structure, it's the self-organization of the plasma energy into the microball lightning that Matsumoto ultimately is saying that it causes the spherical sections to be eaten out of the inside of an electrode. That was observed by John Hutchison, that was observed in experiments that we've done, that forms into this like little star of material which consumes matter, and in Matsumoto's understanding, the most energetic release is the complete collapse of matter, and he argues that the quad neutrons and multiple neutron structures basically decay into a whole bunch of neutrinos and antineutrinos. So there we go. What I like about Edmund Storms, just to close out, is he's still seeking answers, and he's still seeking serious consideration of his thoughts and work. Dr. Edmund Storms, I believe, seriously considered your work tonight in context of prior art, considering further data which you have not looked at, which both supports and extends your understanding of the reaction a step backwards. And for me, my personal view is it's what Matsumoto is suggesting is closer to explaining all of the observables the transmutations at the point of the initial hydrogen catalyzed fusion, and the ability of this type of material to leave the cell or come out of the place in which it is born. And so I would like to have a conversation with you, if that's possible, and discuss this. So with that, I will say thank you, buenas noches, dobro noc, good night.